Learning target 6 says I can identify and correctly use polynomial properties such as degree, leading coefficient, etc. So there are a couple of problems here. The first couple of problems, I give you a polynomial equation, and I'm going to ask you to, from that polynomial equation, identify the degree and the leading coefficient, and use that to figure out what the end behavior looks like. For the second one, we're going to look a little bit more at x-intercepts and multiplicities, and use that information to figure out what the polynomial will look like near those x-intercepts. So for problem number 1, it says for each polynomial below, identify the degree and the leading coefficient, then sketch what the end behavior of the polynomial will look like. So remember, degree means if your polynomial were all multiplied out, all the like terms combined, everything put into standard form with the terms going from highest exponent down to least, what would be the highest exponent on an x value in your polynomial? The leading coefficient is the coefficient on that highest degree term. So the first polynomial I gave you is all written out nicely in standard form, so it's a little bit easier to identify what the degree and the leading coefficient are. So the highest exponent I see with this polynomial written all out in standard form, the highest exponent I see is this exponent of 9. So the degree of my polynomial will be 9. My leading coefficient is the coefficient on that highest degree term. Notice that that is a 10, so my leading coefficient will be 10. Now remember, in class we did a little graphing exploration where you looked at a lot of different graphs and you analyzed what the relationship was between the degree of the polynomial, the leading coefficient, and how the end behavior of the graph looked. And so we found that when the degree was odd, the polynomial will either be going up to infinity on the right and down to infinity on the left, or vice versa. And which situation it is depends on the leading coefficient and whether it's positive or negative. So remember, when it's odd degree, our end behavior will either look like this or like this. This scenario is when the leading coefficient is positive. This scenario is when the leading coefficient is negative. So in this case, we have a positive leading coefficient, so our end behavior is going to go up to infinity to the right, down to infinity to the left. So let's move on to our next polynomial. This one is a little bit harder because it's not all written out nicely in standard form. So we're not going to be able to just see really clearly what the degree is going to be. We can see already that the leading coefficient is -2, but we need to do a little bit of thinking about what the degree is going to be. So let's look at some of these factors. Here we have an x, here we have x minus 1 all squared, here we have another x, and here we have an x minus 4 all squared. So let's just think this through piece by piece. Whenever you have like x plus a number all squared, the biggest exponent that you're going to get from multiplying x plus that number times x plus a number, the biggest exponent on an x will be an x squared. So from this piece, you'll have a bunch of terms, one of which will be an x squared. So we'll get an x squared from this guy. Sorry, that's difficult to read. So you'll get an x squared from this guy. You'll also get an x squared from this guy. Now again, like when you multiply those out, you'll get other terms with just an x or with constants, but the biggest exponent you'll get is an x squared. So you have an x over here from this term, you'll have an x over here from this term, so let's see if we were to multiply everything out, how many x's would we have all multiplied out together to give us sort of the highest exponent on an x? We would have 1 here, another 2 here, that'll make an x cubed term. If we multiply by another x, it'll make an x to the 4th term. And if we multiply by 2 more x's, it'll make an x to the 6th term. term. So our biggest exponent is going to be an x to the 6th. So our degree is just going to be 6. Now this is an even degree. Remember, when we looked at different kinds of polynomials, we found that an even degree polynomial, the end behavior will either go up to infinity on both sides, to the left and right, or down to negative infinity on both sides, to the left and right. And what dictated which of these end behaviors we had was the leading coefficient. We found when the leading coefficient was positive, it goes up on both sides. When the leading coefficient was negative, our polynomial went down on both sides. So in this case, we have a leading coefficient of -2, so it's going to be this scenario over here. And so our end behavior will be that our polynomial will go down to infinity on both sides, on both ends. So problem number 2 says, for each polynomial below, identify the x-intercepts and their multiplicities, then sketch the appearance of the graph near that x-intercept. So looking at this polynomial, notice that it's in factored form for us. So it's not going to be too hard to find our x-intercepts. Now remember, our x-intercepts are where the graph crosses the x-axis. And remember that anywhere along the x-axis, our y value is going to have to be 0. So basically what we need to do to solve for our x-intercepts is to make y be 0 and solve for the x values that make y be 0. So let's do that. So let's say 0 is our y value. And let's solve for the x-intercepts. So notice that this is nicely in factored form for us. So we're going to be able to just use the zero product property from this point. So the first possibility is that 3 is equal to 0, which doesn't make sense. That will never happen. Now, here we have x minus 5 to the third. All that means is that you have x minus 5 happening 3 different times, all multiplied together. So from each of those, you're going to get the same possible x-intercept, which comes from x minus 5 being equal to 0, or x being equal to 5. And we don't have to solve this equation for all 3 separate little factors. We can just do it once. You're just going to get the same x-intercept from each one. Here we're going to have that x plus 1 is equal to 0. And that happens when x is -1. And again, we see that we have an exponent of 2 here, so this factor is really happening twice. It's like multiplied out twice. But we don't need to solve this equation separately for each of the 2 factors. We're just going to get the same x-intercept from it. And then finally, we could have that x minus 1 is equal to 0, and that happens when x is equal to 1. So our possible x-intercepts are going to be where x is 5, where x is -1, and where x is 1. So I'm going to put those in my little table. I usually like to put my x-intercepts going from left to right. So I'm just going to put the -1 first, then the 1, then the 5. So now let's think about what the multiplicity of each x-intercept is. So remember, to find that, we're going to look at the factor that it came from, and we're going to look at what was the exponent on that factor. So looking at our x-intercept -1, that came from this factor here, this x plus 1, and notice that that had an exponent of 2. So my multiplicity for -1 is going to be 2. Next, we have our x-intercept of 1. That came from this factor here, the x minus 1. And notice that has a little invisible exponent of 1 on it. So that will have multiplicity 1. And finally, our x-intercept 5 came from this factor here, the x minus 5 cubed. So that will have a multiplicity 3. Now remember, we saw in class, we did a little investigation and we looked at how the multiplicity of a root or a 0 or an x-intercept, how the multiplicity impacts the appearance of the graph. We found that when a root or an x-intercept has an even multiplicity, our graph is going to touch the x-axis and then turn back around or bounce off the x-axis. We saw that in our little investigation we did during class. So our graph will either look like this, where it touches the x-axis from above and then turns back around, or like this, where it touches from below and turns back around. So that's what our graph is going to look like near the x-intercept -1. Now the x-intercept 1 has a multiplicity of 1, and we found in our investigation during class that when something has a multiplicity of 1, near that x-intercept it's going to cross, it's just going to go straight through. So either like this, or it might look like this. So this is what our graph is going to look like, one of these two possibilities near our x-intercept 1. And finally, our x-intercept of 5, that has a multiplicity of 3. So remember, any kind of an odd multiplicity, as long as it's bigger than 1, is going to make what Simone called an awkward S shape, like this, or like this, near that x-intercept. So that's what our graph is going to look like near the x-intercept x equals 5. So let's move on to part B. So in part B we have this function, -2x times x minus 1 to the 4th times x plus 2 to the 3rd. So the first thing that we want to do is identify our x-intercepts, and then their multiplicities. So some people might look at this and be like, oh, I have an x-intercept of 1 and I have an x-intercept of -2, and they can see that really easily. For those of you who can't, and for those of you who maybe sometimes miss that there's actually an x-intercept of 0 here, let me just quickly go over how you could actually solve for the x-intercepts. So we know that x-intercepts are going to happen wherever our polynomial is equal to 0. So I can set my polynomial equal to 0, and then I can use the zero product property to solve for the values of x that make it 0. So first I have -2x is equal to 0. I have x minus 1 is equal to 0. And I have x plus 2 is equal to 0. And I want to solve for the values of x that satisfy each of these three equations. So for this one over here, I get x equals -2. Here I get x equals 1. And this one is usually the hardest one for people to see automatically from the equation and know how to solve. But all we have to do to solve this equation is divide by -2 on both sides. And 0 divided by -2 is just 0. So I end up with an x-intercept at x equals 0. So my x-intercepts are 0, 1, and -2. Now let's think about their multiplicities. We know that the multiplicity of an x-intercept is the exponent on the factor that gave us that x-intercept. So this factor here is the one that gave us the x-intercept of 0. So let's look at the exponent on the x. Well, 1 isn't written, so that's just going to be sort of an invisible exponent of 1. Remember that anything to the first power is just itself, so we generally don't write that little exponent of 1. But if we just see x and we don't see an exponent on it, that'll just have an exponent of 1. So now let's move to our x-intercept 1. So that came from this factor here, x minus 1 to the 4th. So that will have a multiplicity of 4. And then finally, -2 came from this factor here that has an exponent of 3, so the multiplicity there is 3. So now let's think about the appearance of the graph near the x-intercepts. So based on whether the multiplicity is even or odd and greater than 1 or odd and just equal to 1, that dictates what the graph is going to look like near that x-intercept. So for example, at the x-intercept 0 we have a multiplicity of 1. We know that when we have a multiplicity of 1, our polynomial is going to cross straight through the x-axis at that x-intercept. So it'll look like one of these two possibilities near that x-intercept. Now the next one is a multiplicity of 4, and any even multiplicity, whether it's 2 or 4 or 6 and 8, an x-intercept with that even multiplicity, what the graph will look like near there is the graph will sort of come down and touch the x-axis and turn back around from one of the two directions. So these are our two possibilities for what our graph will look like near the x-intercept x equals 1. And finally, looking at our last x-intercept, we have a multiplicity of 3. And when we have an odd multiplicity that is greater than 1, that's when it's going to make this sort of curvy shape where it sort of evens out close to the x-axis, but ends up actually passing through. So let's just quickly review what we have done in this problem. So what we did was we were given polynomials written in factored form, and we wanted to find their x-intercepts. We wanted to find their multiplicities, and we wanted to find the appearance of the graph near those x-intercepts. And for learning target 6, I might give you, as you saw in the previous problem, I might give you a polynomial and ask you to analyze the leading coefficient and the degree in order to identify the end behavior, or I might give you a polynomial and have you think about the x-intercepts, their multiplicities, and sort of how the graph looks near them.